playable fool for a dad's hire. I was 3 years old.
All right, welcome back. This is lesson 30, channel transitions 2, which is a continuation of what we had last time. We were looking at the delta Z that you need to get channel control, one depth, one discharge. And today we're going to be looking at how to do that by actually contracting the channel. So our learning objectives for today are: explain why channel contractions create hydraulic control, and secondly, calculate the required contraction to establish hydraulic control in the channel. As a quick reminder, this is the last lecture before the celebration of knowledge number 2 that's coming up. So please look at the remaining course schedule that is posted up on Canvas at the beginning of the first page. There's that click here. This is how we deal with coronavirus. Click on that. There's that schedule. So the calculation questions for the celebration of knowledge are going to be as follows. There's going to be the first problem, which is channel river routing. That's worksheet 21. The second problem is going to be critical depth, which is homework 6, number 1, worksheet 27A and worksheet 27B. Hydraulic control, the delta Z, that's going to be focused on homework 6, number 4, and worksheet 29. So the worksheet from last time, calculating that delta Z, that will be the third problem on the celebration of knowledge. And the last one is going to be control structures, which is homework 6, number 2, and worksheet 28A and 28C. That problem will be set up so that you'll have to pick out which equation is correct to use, whether it's a weir or an orifice. Could be conditions where the same structure is doing both things. The way I might have set it up, you'll have to figure out what is happening, if it's a weir or an orifice. Or I could have an example where the same structure actually does both. So please make sure that you're aware of how to do that. So what we're going to look at here today is the following. We're going to be looking at how do you set this B to gain hydraulic control. So this is the same channel we looked at last time. How do you make this B? How wide do you make the channel to gain hydraulic control that way? And this is quite analogous to how the actual gauge and embudo works. We talked about that. The gauge and embudo works because the canyon there, the Rio Grande Gorge, actually pinches the river in and gains that hydraulic control that way, and that's going to be the exact same thing we're looking at today. So, right, we looked at our equations last time, so the equations we're going to use are essentially the same as last time. So we're going to be looking at designing for hydraulic control with a contraction. So how do we make that work? Okay, so last time we had the following equation up on the board, which was our y1 plus v1 squared over 2g is equal to yc plus vc squared over 2g plus z2 plus our head loss from 1 to 2. Okay, how do we make this easier? What can we get rid of in this equation? So if we've got this equation, are z's going to change if we're doing contraction?
Nope.
No, exactly right. That is how we're going to do that. So thank you for that answer there, Brendan. That was excellent. We're going to get rid of this. So z's going to be gone. So we still have our head loss from 1 to 2. So this is our major equation. I'm going to pose a question. So how do we incorporate B? How would we do that, Aubrey? Any ideas? How do we incorporate B?
Could you put a B1 on the left side and a B2 on the right? Or a B1 minus B2?
We could. What are we trying to get? what are we trying to get out of this whole situation? What are we
We're
trying to make
solve
happen?
for B.
Yes, we're trying to solve for a B that makes what happen?
Critical flow.
Yes, exactly. Do we have B in our critical depth equation, maybe?
We have Y.
We do, but we also have B.
Do we?
Yes, we do, because it's the unit discharge, right?
Yeah.
The little Q that we have in our equation, that is the unit discharge. So let's take a look. If we are, I should put a question mark there since this is being recorded and will exist on the internet forever. I'm gonna make sure that our punctuation is right, because that's what we're concerned with these days. All right, so how do we incorporate that? So if we're in a rectangular channel, right? What is our equation? It's YC is equal to little q squared over g raised to the 1/3. Well, what's little q? Little q is simply q over b. So can we calculate this out? Can we do this? Right? All you have to do to calculate the rest of this, so we've got this part here, and it gets really a lot more complicated when you have to do other shapes, but I'm not going to ask you to do that. The FE is not going to ask you to do that. The only time that I've had to do any other shapes was actually for my PE, and it was a hydraulic jump in a trapezoidal channel, and we're actually going to cover that when we get to hydraulic jumps on how to do that with forces. But for now, right, all we have to know is that we're trying to get B into this equation. So this B will go into here, goes into here, and then the great part, if we look at QVA for this setup, okay, if we're looking at QVA, we're trying to get B critical, right? If we've got YC already figured out as a function of B, can we just write that QVA, right? Your area is going to become YC times B. So we've got B in there. We can actually punch that all into a solver and figure out what's happening with our channel. So that provides all the information we need. Now, I've got a nice little trick for you. So, for a rectangular channel, the following has to hold true. E critical is going to be equal to 1.5 times YC. This thing's starting to look good for us here. It's going to be much easier to do than you thought. So, we're going to say that E1, which is this piece right here, has to be equal to 1.5 times YC plus our head loss. Okay, that's as long as we say that our elevation stays constant, and that generally is the case. So if we were solving this for any standard normal channel, what this would look like to actually get the B that we need for critical depth to occur in a rectangular channel, we're going to say Y1 plus V1 squared over 2G. Those will be given, and they're actually given in the worksheet when you're doing that solution. That's going to be equal to 1.5 times, okay, and I'll write this whole entire thing out, right? This is going to be Q over B, so Q squared over B squared divided by G raised to the 1/3 plus whatever head loss is given. So that sets you up for solving this equation quite easily. So what I'm going to do is I'll pull up the worksheet real quick. So when you're doing your worksheet, same type of thing. You're going to say that the channel bottom Z1, Z2 is equal to 0. You set up your energy equation. You should be able to calculate that out to get that your V1 is 2.8 feet per second. Your V2 is going to be an unknown. When you solve your energy 1, it should be 4.12 total feet. Solve for energy 2, you've got your loss given as being 0.1 feet through that whole entire transition. If you set up your E critical like that for your actual calculation, you end up having a B critical that ends up being 2.7 feet and a Y critical that ends up being 2.68 feet. So you can actually go through and calculate the width without actually calculating YC, but on the worksheet, I ask you to do both of those calculations. So if you go through the worksheet solutions posted, you've got all the equations, how to plug that in to actually make this width work for you and get you that critical depth through that actual channel transition zone. And with that, let's check in. Do you think you can explain why contractions create hydraulic control?
Yeah.
Yeah, do these knock energy back, knock you back down that specific energy curve?
Oh yeah.
Subcritical down through that critical point? Sure do. Same way that changes in delta Z do. Can you calculate the required contraction to establish hydraulic control in a channel?
We're getting there.
We're getting there. After the worksheet, you will be there. That is exactly right. So have yourselves a wonderful rest of your afternoon. Make sure to go through all of the homework problems and worksheets that are related to the celebration of knowledge. The celebration of knowledge will be on Canvas. It will open up at 1 o'clock and finish at 2:15 for the conceptual portion and for the calculation portion. The conceptual portion is 20 questions, short answer, multiple choice questions that we will be grading on Canvas. And then for the actual calculation portion, there are 4 questions that you will actually have to do your work by hand using your cheat sheet on your honor. Take a picture of it, upload it, and that's how Jake and I will be grading those. Actually, I will be grading those. So have yourself a wonderful, wonderful afternoon. If you've got any questions, concerns, please reach out to us via email and we'll get back to you as soon as we can. Yes, you had a question, Shelby. What can...
Just to clarify, we have 1 hour and 15 per portion.
Yes.
Okay.
Yes, and I've done that so that you've got 75 minutes for both portions because there's going to be a little more issues trying to quickly type things up, especially with doing 4 calculations plus then having to upload the images and all that stuff. I wanted to make sure that you had a little bit of extra time frame in there to make sure that you can get everything in.
And they'll start on different days.
Yes.
Great.
Yep, the conceptual part is going to be on the 8th of April and the calculation portion is going to be on the 10th of April.
Thank you so much.
You are most welcome, Shelby. Any other questions?
No.
All right. Thank you so much and have a good afternoon.